From probability, the focus moves to using the probability to look at a pattern in the data. That is what we are calling as a distribution. What are the various values which a particular random variable can take, and what is the probability of each of them coming up. So probably in our economy's case, the economy is taking three variables: good, bad, moderate. The probabilities are 20, 50, 30. When I make a tabular presentation of that, which is probably look at it as equivalent to a frequency distribution. All classes corresponding frequency. You made a table. That is what we called as a frequency distribution. The same thing if I do it with a relative frequency, which is what is nothing but a probability distribution equivalent, where you are talking about the various possibilities along with their corresponding probabilities, right? If we are making a tabular form like that, we are calling it as a probability distribution. Just like a frequency distribution, we make a table with the frequencies of each of the class. If we make a table with the probabilities, which is probability is nothing but relative frequency for us. If I take from a sample, if I work on a sample of data, probability is nothing but relative frequency for us, right? Only that aspect of probability comes very heavy into our data related applications, into our statistical data related applications. Whenever we are talking of probability, we may not use subjective probability, or we may not use the a priori kind of a probability here, but we are more looking at usage of empirical kind of a probability. From the past, relative frequency translated to the world of probability. So a probability distribution is actually helping us in listing out the various outcomes along with the probability of their occurrence. So if I make a table something like this, right, what is the outcome and the corresponding probability. This is what we are calling as a probability distribution. And the rules wise, again, all these should sum up to 1. Each one should be between 0 and 1. And all of them should be mutually exclusive. Mutually exclusive. That's the reason when I summing up, it should become 1 main. If there is an overlap, if I sum up, they won't be equal to 1. They may be more than 1 also. So here, this is where what we are doing is we are identifying the outcomes in such a way that they are mutually exclusive as well as exhaustive. And we are trying to define their corresponding probabilities, which can help us in identifying the patterns in the data, which will help us in taking the decisions accordingly. So the probability distribution is the starting point. Once we have computed the probabilities from the data, we are making it in a tabular format, and this is where probably if the number of outcomes are finite in number, like let's say the number of heads when I toss a coin 3 times, probably 0 heads is possible, 1 head is possible, 2 heads are possible, 3 heads are possible, nothing more than that. Or the value that I get when I throw a dice, hardly 6 values are possible. Whenever the number is pretty much limited, countable, finite, we call those kind of distributions as discrete distributions. Whereas if that number of outcomes are uncountable, like heights of a person, right? Depending on the scale which I am using for measurement, if it is in millimeters or micrometers, probably how many values are possible, I'm not sure, right? Even if we are using it in centimeters or millimeters also, the number of outcomes may be countably large. Probably you can sit and count, but it's a very huge number. Whenever we are seeing that the number of outcomes are countably large, we call those kind of variables as continuous variables. And where the numbers are finite, where they are countable, so something to do a counting process, we call them as discrete variables. Something which cannot be counted, but they are more like measured, time related, depending on the hour, minute, second, which I am choosing as my unit, probably the number of outcomes will be more in number, countably large. But that cannot happen with a throw of a dice. I cannot get 1.2. I cannot get 3.6. I'm sure that I will get only one of the six possibilities. Right? So they go under discrete. Whereas if the numbers are countably large and something relating to time, the rates of return, again, if I am taking it as an integer, 1%, 2% kind of numbers, then probably they are countable. But in reality, 1.234%, like that, if I am taking, they are relatively large and I cannot count how many such returns are possible. Right? Each could differ by 0.001% also. So they become continuous, whereas which can be counted becomes discrete. Why we are talking about this again? Depending on what we want to predict. If we want to predict a discrete variable, like what is the chance of getting a profit on 2 out of the 5 days? In the next 1 week, what is the chance that I will make a profit in 2 days? Or in at least 2 days? There, I'm talking about modeling the count. Either it could be 2 days, 3 days, 4 days, 5 days. It can never be 2.2 days in that case. So, for modeling or for finding out the probability of those kind of questions, we have to resort to the discrete distribution patterns. But let's say if the question is, what is the probability that the loss is more than 20% for the next 5 days? What is the probability that the loss is more than 20%? In that case, I don't know, it could be any number, 20.1, 20.12, 20.123, any percent is more than 20% itself. So I'm not sure how many outcomes are possible. So anything to do with the calculation or a measurement kind of stuff, we use continuous random variables and continuous distributions for them. But if my objective is to find out the probabilities associated with the counting kind of stuff, we use the corresponding discrete kind of distributions. There are some, of course, there are so many distributions that are floating in the world, but the most common of them which we typically look at are very few as far as our courses are concerned. And in a continuous, one important point for us is, because the number of outcomes are countably large, the probability of one single outcome coming up is almost negligible. Right? Favorable is 1. Total outcomes is very large. Let's assume some 1 lakh. 1 by 1 lakh. Point not 1 is the, because the favorability is only one particular item occurring. Right? So generally in case of continuous, people never talk about probability of one outcome occurring. They look at it as probability in a range of values. What is the chance that the returns are between 1% and 2%? They'll never, if the question comes out, what is the chance that the returns are 1.234%? Then I can write it as 0. But if it is asked as what is the chance that they lie between 1.2 and 1.4%, then I can try to find out. Because in case of continuous distribution, the probability does not exist for a single pointed value. It is always for a range of values itself. That's one thing which we have to be comfortable with. And once we make a distribution, on that distribution, we create a function. Function is nothing but the representation, the generalized representation of that distribution. What do I mean by that? Let's say if my probability is, let's say dice 1, 2, 3, 4, 5, 6, and the corresponding probabilities are 1 by 6 something. When I say I'm writing a probability function, the way I write it is P of x equal to x or equal to 1 by 6, where x is equal to 1, comma 2, comma 3, comma 4, comma 5, comma 6, and it is equal to 0 otherwise. What did I write here? I am saying the probability that the random variable x, my random variable is this x. The probability that my random variable x takes a value equal to 1 is 1 by 6. My random variable x takes a value equal to 2 is 1 by 6. So, the same thing, if I write it in this form, we are calling it as a probability function. Whether it is for discrete or for continuous. So, if I write, let's say if a function is given to me like this, probability of x equal to x is equal to x by 10, where x equal to 1, 2, 3, 4 and 0 otherwise. What is my probabilities now? My x is 1, 2, 3, 4. What are the probabilities? Is given x by 10 is the probability. So for 1 it is 1 by 10. For 2 it is 2 by 10, 3 by 10, 4 by 10. Is it a probability distribution? First of all, the sum is equal to 1. Each one is lying between 0 and 1. If these two are not coming out, then whatever the formula he is writing, it's not a probability distribution. The question, some silly questions would be given for us on these lines. He'll just say something, okay? Probability of x equal to x by 10 for x equal to 1, 2, 3. This is not a probability distribution at all. Because even if you take it as 1 by 10, 2 by 10, 3 by 10, their sum is not equal to 1. If the sum is not equal to 1, it's not a probability distribution at all. Or sometimes he may give, in one of the probabilities, he may give a negative value. Even that would not be a probability distribution because probability can never be negative. It lies only between 0 and 1, both inclusive. Right? So, 1 is the probability function, either represented as p of x, small p. For a discrete, generally we write it as p of x. For a continuous, we write it as f of x. So, when I say p of x, it means, or when I say p of 2, it means the probability that x takes a value equal to 2. That is meant by p of 2. The probability that x takes a value of 2 is sometimes in short written as p of 2. So